won't take but a minute or two, and then we'll start chapter 10. All right, so Chemistry 3101, we finished up our review on alkynes last class. We did a whole bunch of practice problems from Klein, but there is a couple of questions that I wanted to take a look at with you this morning, just so you remember these. And these are the kind of questions that they like to ask on an ACS final, quizzes, MCAT exams, anything like that. So you can see that the two questions that I have are shown here. The first one is, if we start with 1-butine, how do we make this meso compound? So this would be a meso compound here. And then the second one is not a meso compound, right? So in the second one, you end up with this compound where you have one bromine going in the back and one bromine coming out in front. And so, of course, you could have an enantiomer of that compound as well. So how would we make that compound plus its enantiomer? So I thought we'd start with the first one and do a retrosynthetic treatment of it. All right, so we'll start with the first one. And just by way of retrosynthesis, could anybody remind me, the only way that we know how to add two bromines is by treating a double bond, an alkene, with bromine. And is bromine addition, is that an anti-addition or a syn addition? Could anybody answer that? When I add bromine to a double bond of an alkene, does it add in a syn fashion or an anti fashion? And you can type your answer into the chat. Yeah, it's an anti-addition, right? So if it's anti-addition, so let's just erase this and we'll put anti-addition. That would mean that I can't start with the cis alkene, right? I cannot start with this compound, right? Because that would make this compound. All right. And so what I need to do is I need to start with the trans compound. So I want to make this compound. Okay, if I can make the trans alkene, then I can do an anti-addition, and then I will get a meso compound. And if you're not completely sure about that, I'll review that with you as to why that is. So let's take a look at how we would make this alkene. Well, you can see that we're starting out with a compound that has 4 carbons in it, and we need to make an alkene that, of course, has 6 carbons, and our final product has 6 carbons. So the first thing we're going to need to do is we're going to need to add 2 carbons. And the only place that we can do that is on the terminal alkyne. We can do a deprotonation with sodium amide. So I'll just put here NaNH2. So that does our deprotonation. And then we can alkylate with ethyl iodide. And if you put ethyl bromide or ethyl chloride, that's fine too. And so that will give you 3-hexyne, this molecule here. Okay, so that gives you 3-hexyne or hex-3-ine. Either way is totally fine. I didn't mean to rhyme, but here you go. All right, so now if we want to take that compound and we want to reduce it to the trans alkene, right? I'm trying to get to the trans alkene. Could anybody suggest reaction conditions for that? How would I reduce it to the trans alkene? Even if you just give me part of the reagents, I'd be cool with that. How do I reduce to the trans alkene? What reagent would I need? I'm going to have to do a sodium metal reduction, right? So I'm going to use sodium, and I'm going to put that in liquid ammonia, and that's going to reduce the alkyne to the trans alkene. So that gives me the trans alkene, like this. Again, this is trans. So this would be trans 3-hexene is the name of this compound. And now if I do the bromine addition, right, if I treat this with Br2, so just some bromine, that's going to add in an anti-fashion. So let's write that down again, that this is an anti-addition. So what's the product going to look like then? Well, if I draw all these carbons in the same conformation I started with, I'm going to have one bromine going down like this, okay, behind the screen, and I have another one coming out in front. So the question is, are these two compounds the same? The answer is yes, they are identical. So how do you figure that out? Well, what you're going to have to do is you're going to have to rotate this bond 180 degrees. And when you rotate that bond 180 degrees, what you're going to see is this bromine that was coming out or going behind the page is now going to be coming out in front of the page like that. Now, there's a couple of ways you could do this. I suppose there's 3 ways. You could do it with a molecular model kit. That's one way. You could do it by drawing a Newman projection, but the best way is to just familiarize yourself with the idea that if the bromine is going behind the page, that means that you have a proton coming out like this. And so if I rotate this bond 180 degrees, okay, 180 degrees, when the ethyl group is coming down, or if you want to call that an ethyl group, okay, when that's pointing down, then the hydrogen and the bromine are going to be on the top, but they're going to have switched positions. So now the hydrogen is in the back, like this. And so you can clearly see now that these two compounds are identical. So this compound here and this compound here, they are the same compound. This is the meso compound. Give me a thumbs up if you follow me on that. Everybody with me on that idea? Or stop me if you have a question. Okay, cool. So make sure you remember the sodium metal reduction is how we reduce an alkyne to a transalkene. All right, so let's try the other situation, and that is where we want to take 1-butyne. So we'll start with 1-butyne again, and now we want to make this compound where we have 1 bromine coming out towards you, and we have 1 bromine going away, like that. So since we know that bromine does anti-addition, right, what's our starting material going to be this time? It's going to be the cis alkene, right? So we have to start with the cis alkene. Now, again, we're starting out with something that has 4 carbons, and we have to add 2 more carbons to make a total of 6. So the only way we know how to do that is the same way that we did in the last problem. We treat it with sodium amide to do the deprotonation, right? That rips off the terminal proton. That makes an alkanide, and then it does an SN2 with ethyl iodide or ethyl bromide or ethyl chloride. So that gives us our 3-hexyne molecule, which looks like this. And now we need to reduce this to the cis alkene. So we're going to treat this with hydrogen. And can anybody tell me what else I need to reduce this to a cis alkene? Excellent. Absolutely. It's a poison catalyst, like Lindlar's catalyst. So we'll put here Lindlar's catalyst, like that. And now we know that since the bromination is an anti-addition, all we have to do is treat this with bromine, and we're done. It does an anti-addition, and there you have it. All right. So the reason I went over these 2 specific problems with you this morning, the only one that's in the book, I think, is this one. I'd have to double check. But because the authors of the textbook like to ask these kind of questions in homework, and like I told you, they can show up in any kind of standardized exam. All right. So the other kind of problem that you'll see that's in the same vein of this problem is if you're making a diol, right? So we learned how to do a syn dihydroxylation and anti-dihydroxylation. And so you need to be able to use those reactions as well in order to make meso compounds and then stereoisomers. And of course, you know, here you would also end up with the other stereoisomer, which would be the enantiomer. I didn't pencil it in there. But there you go. So that covers chapter 9. And again, if you have any questions about this chapter, feel free to email me and ask me anything you want to ask me.